Hello, this is Mr. White, and this video is on finding the area of a region between two curves. Here are the two exercises for today. And before we dive into those exercises, let's just recall real quickly the concept that you're presumably introduced to in class. So I'm just going to recap it here very quickly. Let's say you had some function whose graph looks like this, and we'll call that function f. And if we focus on the region between x values of a and b, then the area under that curve is represented by this integral, this definite integral. Now, if any part of f of x were below the x-axis, calling it the area under the curve might be problematic, but this concept will still hold for the video. So let's now consider some other function, g. Let's say g looks like this. And again, for sake of discussion, I'm depicting g as if it were completely above the x-axis on that interval. And its area would be as such, with this definite integral. So if we ask ourselves, what would happen if I took all this red area, represented by the red integral, and what if I subtracted from that area all this green area, represented by the green integral? Well, what I would be left with is this area, represented by this first integral minus the second integral. And since the limits of integration are the same between those two integrals, we could also combine them into a single integral from a to b of f of x minus g of x dx. So it seems most students don't have too much trouble with that concept. And as long as the a and b values are given to you, and you recognize that the f function is completely above the g function, and therefore we do f minus g. With all those little caveats, I expect you won't have too much trouble. But here's where the problems typically occur. Let's say that a and b are not given to you. They're not provided. And furthermore, let's say a picture is not provided to you either. And it's not clear to you whether you should have f minus g or whether you should reverse and have g minus f. Well, that's what we're going to try to deal with today's exercises. So notice that in neither of these two exercises are you provided the limits of integration, nor are you provided a picture. So let's see how we're going to handle that. All right, well, again, we're not provided a picture here, but this is a very graphical, visual topic within calculus, so you absolutely should draw a picture. You probably knew I was going to say that. And looking at these functions, they're not terribly complicated. Our pre-calculus skills will help us out. We know that f of x is a parabola, a basic parabola, x squared that goes through the origin. However, it's been translated up 2 units. So 1, 2. And we know g of x is just a line. It's presented here in slope-intercept form, so we know it has a y-intercept of 0, 5 right here, and we know it's got a slope of 2. Now, I don't feel the need to draw this super precisely. I'll just draw something with a general upward slope. And we can see visually right off the bat that there are going to be 2 points of intersection. So now we understand why we didn't have to be provided our a and b values. We're going to find out what these a and b values are that completely bound a closed region between these two curves alone. So again, just to make sure you see this bigger picture, if f and g don't intersect, then you don't have a closed region between those two curves. You're going to need an a and a b value provided to you that will provide those additional walls needed to bound the region. But as is the case in our functions here that we just sketched, the two functions alone completely bound the region. So our next task is to find a and b, and we'll do that by algebraically setting f of x equal to g of x. Or let's go ahead and put f of x, x squared plus 2, equals 2x plus 5. Let's subtract everything over to one side. So we'll have x squared minus this 2x. And then we got plus 2, and we'll subtract the 5 over to the left. That'll give us minus 3. That'll leave us with 0 on the right. We factor this. Turns out to be not too bad as far as factoring goes. We know we'll have a 1 and a 3, and it looks like this needs to be a minus and this needs to be a plus. So that means that x equals -1 or positive 3. And looking at our picture, that seems reasonable, that this a value is -1 and this b value is positive 3. So in addition to verifying for us that we were going to have some intersecting curves here, what this picture did for us, what our sketch did for us, is it allowed us to see, would we have f of x minus g of x in our integral, or would it be the other way around? Well, looking at the picture, we see visually that g is above f on the interval that we're interested in. So that tells us that we need to have the g subtracting the f. And of course, on this integral, I need to put the limits of integration, now that we know them, -1 to 3. So let's scroll down just a little bit here, and we'll rewrite the definite integral from -1 to 3 of g of x, 2x plus 5, minus f of x. Now let's go ahead and just distribute that negative sign. So minus, we could do parentheses x squared plus 2, close parentheses. But let's do minus x squared minus 2. We've just gone ahead and distributed the negative. Then dx. All right, before we do our FTC, let's go ahead and combine like terms. So -1 to 3. If you're like me, you just by habit put things in standard form. So we'll put the quadratic term first. You don't have to, but I'll choose to. Plus 2x plus 5 minus 2. That's going to be plus 3. And this is familiar FTC territory, so I'll speed it up here. We anti-derive. The negative x squared becomes x cubed with a 1/3 and a negative. We have plus x squared plus 3x from -1 to 3. And if I plug in 3 into this first term here, -1/3 times 3 cubed, that's -27 over 3, or -9. Onto the second term, plus 3 squared, plus 9, plus 3 times x value of 3, plus 9. 3 nines, feels like a jackpot or something. In any case, let's put that in parentheses, and let's subtract. That's sort of like our big F of x, or our big F of b, and now we're going to do our big F of a. I'm using our FTC terminology here. So I plug that -1, and let's be careful these negative signs. -1 cubed is going to be -1 times a -1/3 is going to be positive 1/3. Probably already found by now that those negative signs can really trip you up on the FTC. We'll put a -1 squared, that's going to be a positive 1. Plus 3 times -1, that's going to be minus 3. All right, -9 plus 9 goes away. We've got 9. I'll distribute this negative. Minus 1/3, minus 1, plus 3. 9 plus 3 gives us 12. Minus 1 gives us 11. 11 minus 1/3, that gives us 10 2/3. Now I'll write it down, but we really prefer not to leave mixed numbers as our final answer in general. So that's the same as 32/3. So let's do a quick calculator verification. With these window settings and the equations entered, you would see this on your display. And again, we notice that y2 was the upper graph and y1 was the lower graph. So with that in mind, you would type into the calculator as follows. Again, taking care to do y2 minus y1. And of course, it is much prettier on the newer TI-84s, but TI-83s still get the job done for this kind of task. Okay, let's go on to the next exercise. Okay, similar to last time, we've been provided two equations, no limits of integration, and no picture. Unsimilar to last time, this is certainly not just a simple transformation of one of our basic pre-calculus functions. However, the thinking that we developed back in pre-calculus and in your earlier years will still help us come up with a sketch here. Let's start thinking of domain. And my clue there was looking at the radical there. That often restricts our domain. So think of what values you can and cannot plug in for x, and still get a real output, of course. If I tried to plug in x equals 5, I can see that, again, due to the radical, I'm going to run into trouble. I'm going to get square root of negative 24, and we're not dealing with that this year. No imaginary numbers in AP Calc AB. Even a relatively small number like 2 still poses problems. It looks like 1 is at the edge of the domain there. We can just barely plug in a 1 there, and we'll get square root of 0. And in fact, I see that by plugging in x equals 1, I would then get a y equals 0 in return. So that would be an x-intercept right here at 1, 0. We try a little symmetry. How about negative 1? Well, the same thing occurs at negative 1, right? We get 0 as an output. So another x-intercept at negative 1, 0. And in fact, we often find that 0 is an easy number to plug in itself. And we see that even though this factor now no longer equals 0, that 0 out in front is going to produce a y value of 0. So we've got another x and y intercept at the origin. And while from here at this point, if we really wanted to be rigid and thorough about it, we could do things like finding extrema, minima, and maxima using the first derivative test, second derivative test, whatever. We don't need to be that fancy here today. And I think it could be argued that a really useful skill in calculus and math in general is knowing when you really need to be rigid and thorough and when you just need kind of a ballpark estimate, just a rough figure here. So let's just plug in something halfway between 0 and 1. Let's plug in 1/2. That would give us, let's see, 1/2 times the square root 1 minus 1/2 squared would be 3/4, right? And if you're really in the mood just for some ballpark estimating, we might say, okay, that's about equal to 0.5 times square root of 0.75. In fact, that's not only about equal, that's exactly equal. But what it's about equal to is 0.5 times square root of 0.81. Now, if you're wondering where in the world did I get 0.81 from, it's because I'm just trying to do some mental math and some approximating. And I know that that 0.81 is the square of 0.9. And if I've got 0.5 times 0.9, I know that that's going to give me 0.45. So what did all that buy us? Well, it told us that when I plug in x equals 1/2, I'm going to get an output that's a little bit less than y equals 1/2, somewhere around there. Now, is that a maximum, a local maximum? I don't know. The graph could have a maximum before x equals 1/2, or it could have a maximum after. But just for what we're trying to do, we're trying to get a rough shape. So let's just sketch something kind of like this. Let me get these calculations off the screen here. And if I examine the symmetry of this graph, if I ask what happens if I plug in a negative 1/2 here, I would notice that I would just get the opposite output. I would get negative 0.45-ish or so. I could tell I'm dealing with an odd function here. Again, that's one where generally plugging in any negative x is going to be the opposite of plugging in the positive x. So the less motivated student is, of course, just going to grab a calculator and ignore everything I've said here. But if you're willing to practice your mental math and just kind of knowing when it's appropriate to approximate, it'll be good practice for not just skills in this class, but later on math classes. Okay, so that was this graph. We don't have them labeled F and G here. You could label them that way if you want. Let's just color code that one green. Thankfully, that one's a lot easier, right? That's just a line through the origin with the slope of 1/2. So it's going to look something kind of like this. And now we can tell that as far as region bounded by these two curves alone, we're really not dealing with just one region, we're dealing with two regions across from each other, across the origin. And while we can tell that one point of intersection of those two curves is at the origin, we need to find these other 2 points of intersection, which we'll call A and B for right now. So rather than find A and B right away, I just feel like writing the integral right off the bat. We'll find A and B next. Okay, for this region over here, that little intersection, we'll have the integral, and it'll go from A all the way to 0. I'm only trying to capture this part of the area for right now. And over that part of the area, notice that the green curve is above the red curve. So I'm going to list it in the appropriate order. The green curve minus the red curve. And if we shift our attention to the other half, we notice that over here, we'll add that area. This time we'll go from an x value of 0 to an x value of b. But this time it's going to be red curve over the green curve. So for the integral, we'll put red curve or red equation minus green equation. So that's something you're typically going to have to do when you have one curve crossing another curve, and where the one that used to be on bottom is now on top, and the one that's used to be on top is now on the bottom. Now in this case, this doesn't always happen, but in this case we're a little bit lucky. Due to symmetry, we know that that area over here on the left is exactly the same as this area on the right. So what we can choose to do is take either one of those pieces and double it. So why don't we take the second piece, the second integral, and we'll say that adding those two integrals together is the same as just doubling either one of them. And in this case, we just arbitrarily chose the second one. So this is the point where I really have to now solve for that limit of integration. I need to find out what this b value is so that I can then go ahead and FTC this thing. Of course, we find intersection points by setting one curve, the red curve, x1 minus x squared, equal to the other curve, which in this case was 1/2 x. Let's clear ourselves a little room. Let's move this down here. And as much as I hassle students about poorly organized work, I'll admit this is not my best organization, but trying to keep it all visible on the screen here is tough. Any case, let's start by squaring both sides. That'll get rid of the radical. So if I square the x, I'll get x squared. If I square the radical, I'll get 1 minus x squared. And if I square the right side, I will get 1/4 x squared. Rather than distribute out that left side, let's subtract the 1/4 x squared from both sides, giving us this resulting equation. And then from there, we can factor out the greatest common factor, x squared. And on the inside, we'll get 1 minus x squared, and then minus 1/4 equals 0. That will give me x squared times 3/4 minus x squared equals 0. And that will give me an intersection point at x equals 0. We already knew it intersected at the origin. And we'll get our other two intersection points at x equals plus or minus square root of 3 over square root of 4, which is just 2. So that's a ratio we dealt with a lot back in our unit circle days, right? So plus or minus root 3 over 2, you may recognize that's about 0.866, plus or minus 0.866. So now we know that this intersection occurred at negative 0.866-ish, and this was at positive 0.866-ish. And on to the definite integral. So we now know our limit of integration. I'm going to just bring this down, and maybe this is a little bit lazy of me, but I'm going to cover that up and say we now know that this is the positive square root of 3 over 2. And since this is basic FTC stuff, I'm going to try to, well, this also looks like an unchained rule in there. I'm going to speed up here a little bit. I'm going to split this into two separate integrals. One for the first term and one for the second term. Let's actually get this out of here. And let's write this in a little more calculus-friendly way. Okay, there, like that. And notice that this fits the unchain rule pattern. We've got a function inside of this blank to the 1/2 power function. And the inside function has a derivative of negative 2x. So that's what we want sitting right beside it, the u prime, so to speak, or the g prime of x if you prefer. So let's move this over a bit, and let's bring that 2 on into the inside. And since we want a negative 2x, I'll put a negative inside and outside. And as far as this 2 and this 1/2 over in the other integral, let's let them multiply or cancel each other out. Now I'm going to anti-derive. I'm going to unchain rule the first integral, and I'll get 1 minus x squared. Instead of the 1/2, that gets raised back up to a 3/2. We have a 2/3 in front to balance it out. This chain goes away, but the negative in front comes along for the ride. As far as the second integral goes, I'll anti-derive x, and we'll get 1/2 x squared. Since these do have the same limits of integration, I'll join these back together. I'll put a minus sign there. We'll go from 0 to root 3 over 2. And now it's just time to plug in. See, plug in the root 3 over 2 here and here. And that's going to give me that. Let's now look at the 0. And be careful, that doesn't automatically give me a bunch of zeros. Notice that this term over here will not be 0. I'm going to get negative 2/3, then minus 0. And if I simplify all that, I get all this, which is 5/24, or if you prefer, about 0.208. Well, let's go ahead and put 3 repeating decimal. All right, that one was a bit of a handful. Hope you caught all that. Here is our calculator verification. And notice that I'm using this snazzy trick that I've probably shown you in class involving absolute value bars and not having to, and then writing it as one integral. I'm not going to take the time to explain that here, but I suggest you ask if you missed that or if you didn't completely understand it. Okay, let's call it a day for this exercise.